And recording is running.
Awesome. So hi, everybody. My name is Rosina von Schaffhausen in the SCA, or Victoria Sapko mundanely. There should be a link in the chat window for the handout. Please feel free to link to that in Google Drive, download a copy if you want. And the last page in the handout is an appendix that contains a translation. I didn't do the translation. It's from a copy of the translation of Fibonacci's main work, but it's the translation of the rabbit problem, which is where the Fibonacci sequence appears in his writing. So that bit is a cool bit to read, and gives you an idea of what his writing was like, what he wrote about the Fibonacci sequence, and kind of the idea of what writing about mathematics in general was like at this time. It's most of the symbols that we use today weren't being used yet. Most of the a lot of the terms that we have today weren't being used yet. It's very much describing everything in words and using very little symbols, which is very different from how a lot of people feel about math today. So it's kind of a different thing. I am going to present to you some slides here. Oh, what did? All right, I think my slides just decided to. There we go. Okay. So please do let me know if something goes wrong with the slides, because I'm now at the point where I can't see any of you. Can you all see my screen and the first slide with the title?
No.
No? It's
No.
still doing the camera?
Doing the camera.
All right. I see. Okay, now I think it's working. Do folks see my screen now?
Yes.
Yep.
Excellent. Okay. Oops. Move back. Okay, so the real Fibonacci numbers. So what we're going to talk about today, we're going to talk about the Fibonacci sequence, but we're also going to talk about another sequence of numbers that Fibonacci studied in depth, and look at the two of them and what Fibonacci wrote about them, what he knew about them, evidence that we have about these sequences from other mathematicians in the Middle Ages and earlier, and see what which sequence really should be the one that we name after Fibonacci, because I'm not sure that the Fibonacci numbers, what we call the Fibonacci numbers today, is the right one. So we'll take a look at the evidence and see what we get from all of this. First of all, let's talk a little bit about who Fibonacci was. He's a really interesting guy for a number of reasons. He lived from roughly 1170 to roughly 1250 in the city of Pisa. He also traveled a number of places around the Mediterranean, and some evidence of that is in his books. He was active mathematically from roughly 1202 to 1228. All of the books that he wrote that we have are from that time period, mostly in the 1220s. It looks like he may have taken a break for nearly 20 years before he got back to mathematical writing. after he wrote his first book. And his real name was not Fibonacci. As he put it in one of his books, he listed his name as Leonardo Pisano Bigolo. So basically it's Leonardo of Pisa, with the name Bigolo is a byname that probably means traveler. A later meaning of it is good for nothing, but considering that another place where that name appears is in an award given to him by the city of Pisa in 1241, it wasn't a negative thing at the time. So any negative connotations of the name Bigolo were not in existence at that time. He also signs his name as Leonardo Pisano Filius Bonacci in his magnum opus, his big book Liber Abaci. And that the Filius Bonacci actually means of the family Bonacci. And Bonacci was probably the name of a famous ancestor. It wasn't his father's name. His father's name was Guglielmo, from the evidence that we have. And it wasn't his father's nickname, probably. Actually, it was probably his brother's name, and most likely it was his brother was named after a famous ancestor. The name Fibonacci is a modern name contracted from Filius Bonacci by 19th century mathematicians who did not want to just call him Pisano, because there were plenty of people who were who used that name from the city of Pisa in the Middle Ages, and it didn't really delineate him from a whole lot of other people. So they gave him a last name because they were kind of offended by the fact that he didn't have one. So it's the modern name. It wasn't anything that he ever used. Most of his writing is about our modern number system. Basically, when he was young, his father had him sent to North Africa. His father was working in North Africa he was in charge of a Pisan trading house on the North African coast. And he had Leonardo sent to him, young Fibonacci sent to him, and had him study under all of the scholars that were going through the port. And that's where Fibonacci discovered our modern number system and realized that it was a much better system than what was in use in Europe. And so he wrote his books towards merchants and to try to convince them to use the Hindu Arabic numerals and instead of Roman numerals, and to use the algorithms that we have rather than an abacus. So an abacus is really great for addition and subtraction. It's not so great for more complicated things like multiplication and division, and it doesn't work well at all for square roots, as far as I know. And those are some things that become more and more important as in order to be able to solve problems that come up with the use of corporations, because the first corporations were being established at that time. He actually talks about them in his books, about how to divide profit between a number of investors in a corporation. I mean, the number of investors he has is usually not very large. It's usually less than 10, like less than 5 or 6 most of the time even. But it's useful to see where corporation use was starting up, and how it was seen as our modern number system was useful for solving real problems that people had at the time. The other thing about him that is really cool is that he was the only European to do original research in the Middle Ages that we have any real evidence of. All of the other Europeans, so he was that means he was the only person in Europe to solve new math problems that other people hadn't solved before. And his original research is some of what we're going to talk about today. Really the only, and when I say he was the only European to do this in the Middle Ages, basically from the ancient Greeks and the fall of the Roman Empire. So there were folks doing math throughout from the ancient Greeks and throughout the Roman Empire. They were solving new math problems up until about the fall of the Roman Empire, and then there's nothing else until the Renaissance. And only in the late 15th century and early 16th century do we get new original research that we see happening in the Middle Ages that is in any way useful and important. So he did start some schools of mathematics that followed him, but they didn't really do a whole lot until the Renaissance started up. That's when we really get original research happening and being lively in Europe again. So that's the big thing about him, is he's basically the only person that we have evidence that he did original research and that it was in any way important or useful for other mathematicians or for real world problems. So what is being weird? I haven't used Google's slides before, so this is kind of interesting. I'll see how it works out. So let's talk a little bit about the Fibonacci sequence. A lot of people know quite a bit about it. It's the numbers 1, 2, 3, 5, 8, 13, 21, 34, etc., and so forth. Modern mathematicians tend to put 2 1s at the beginning of it, but Fibonacci didn't have that. If you look at the rabbit problem, the 2 1s don't appear. It's just 1, 2, 3, and so on. So that's what I use when I'm talking about the Fibonacci sequence. And basically, to get the next number in the sequence, all you have to do is add the previous 2. So 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, and so on. And you can get all of the numbers in the sequence just adding the previous 2. It's called a recursive sequence because you use the last number or 2 to get the next one. And it's a really cool sequence because modern mathematicians have proven many, many facts about Fibonacci numbers and their relationships to other numbers. If you take a look at MathWorld, mathworld.wolfram.com, their page on Fibonacci numbers is long and has huge numbers of equations relating Fibonacci numbers to other ones. See if I can show you briefly. Here we go. Also including a very cute cartoon there at the beginning. But if you scroll down through here, there's a large number of equations that relate to the Fibonacci numbers. We're going to talk about some of these equations in here a little bit later, just very briefly. And then there's just tons of these relationships where here, basically, this says that if you add up all of the Fibonacci numbers to a certain point, it's equal to the Fibonacci number 2 points after that minus 1, which is really cool. And then this one in here gives you a bunch of interesting relationships between different Fibonacci numbers. There's a whole bunch of more equations in here. Tons and tons and tons. Here's a really cool one that was actually just published in 1989. That if you look at the shallow diagonals of Pascal's triangle, the Fibonacci numbers show up, which is really cool. I love these diagonals. Kind of neat. So there's more and more that you can find. One of the things that they mention right here is the Fibonacci Quarterly Journal. That's a journal that is dedicated just to the Fibonacci numbers, related mathematics, and also the history of Fibonacci. They occasionally will publish history articles on Fibonacci and things relating to him. So it's a really cool journal, and this particular resource is a Wolfram Math World is a good modern resource, online resource that is freely available about modern mathematics. It has some about the math history, but it's more of a reference for modern mathematics. So back to this, to the slides. I mentioned one of the this is having so one of the relationships that I like to point out is this one, the successive ratios of two Fibonacci numbers converges to the golden ratio. So 2 divided by 1 is 2, 3 divided by 1 is 1.5, 5 divided by 3 is 1.66666, and that one's an infinitely long non-repeating repeating decimal. 8 divided by 5 is 1.6. 13 divided by 8 is 1.625. And these are all getting closer and closer to the golden ratio, which is 1.61828. And then it's a very long decimal, but infinitely long decimal. But it's equal to 1 plus the square root of 5 over 2. This number is called the golden ratio, and it's really... it's one that people believe is very important in aesthetics and was important to the ancient Greeks. It pops up in some of the Renaissance writings of some of the Renaissance mathematicians. It's very interesting. And people also believe that Johannes Kepler knew about this relationship in period. So that's why I like looking at this particular fact about the Fibonacci numbers. Is that it was probably known in period, unlike a lot of the other modern facts. So so that one's one that another thing that happens is that Fibonacci numbers tend to appear in nature. First of all, they appear in a lot of plants. Here's a pine cone. And the picture of the pine cone, if you notice, if you look at the individual knots on the pine cone, in one direction they make swirls that go out clockwise. You can count that there are 8 swirls going out that way. 1, 2, 3, 4, 5, 6, 7, 8. And then if you look at the counterclockwise swirls coming out from the center, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 swirls going the other direction. So that whole idea of the two numbers of swirls appears in a lot of plants. And the 2 numbers being Fibonacci numbers appears on a lot of plants. So pine cones are one, pineapples are another. Pineapples, you can actually get 3 sets of swirls because they've got hexagon shaped pieces. So there are 5. I'm sorry about the very blurry numbers there. This should be a 5, but it's blown up so big you can't really see it. There's 5 rows of swirls going around. So if you get down to like this one here, it's actually part of the same swirl as the one at the very top, just wrapping all the way around the pineapple. For this one here, if you look at pineapples in a different direction, you'll get 8 swirls, and then from another direction, you'll get 13. And not all pineapples will do it exactly, but they'll be pretty close. I've actually gone to grocery stores and tried to hunt these down for students in the past and to bring to a class and show, hey, here's a pineapple, and here's the 5, and here's the 8, and here's the... And it doesn't work quite as well as I would have liked with actual real pineapples from the store. But you can find them that do work this way very nicely. And this picture, I think, fell off the handout. I had it in my version online, and then when I converted it to a PDF to share with everybody, it ended up that this picture fell out. But
no, it's in the handout. It's in the paper.
Okay, good. So this one is the center, shows the center of a daisy, the seeds at the center of the daisy, and shows that there's a different number of swirls going in each direction. You'll find that also in other plants like sunflowers. Sunflowers usually have like 89 to 144, sometimes as high as 231 swirls going in one direction. A former colleague of mine actually used to have an old dried dandelion sunflower head in his office with the painted to show how many, like every 10th swirl was painted in each direction to show how many there were. It was kind of cool. So the Fibonacci numbers also form a spiral. The Fibonacci spiral, basically, if you take a square of each side, where the side length of each square is a Fibonacci number, then you'll make a quarter circle from one corner to an opposite corner inside the square, and then line the squares up this way. They turn into this very nice, pretty spiral. Now, if you notice over here, this the hurricane lines up with the spiral pretty well. So does this galaxy. This shell doesn't line up very well with the spiral, though. If you Google Fibonacci spiral in nature, you'll get a lot of shells, but a lot of the shells are actually logarithmic spirals and not Fibonacci spirals. If you notice, this one doesn't fit that well at all. Like, it's close to the edge out here, but it's way far from the edge as you get in closer. It doesn't line up quite as well as you would hope that it would. This one doesn't seem to fit terribly that well at all. That's why I included that particular picture, because you can't trust every Fibonacci spiral picture that you see, basically. But there is evidence that these spirals do appear in places in nature. Another place where they pop up is in bee genealogy, and this was possibly known in period. Arab beekeepers in North Africa were doing quite a bit of beekeeping and studying the science of it as early as the 9th century. So it is possible that this was known to Fibonacci and that he knew about this. And it may be where he got the rabbit problem from. But it's pretty cool. The reason it pops up this way is because male bees only have one parent, the female parent, but because they come from unfertilized eggs. But female bees come from fertilized eggs, so they have two parents. So if you look at each generation, each generation has a Fibonacci number of bees in it. So this generation has 2 bees, but the next generation has 3, and then the next 5 and 8 and 13 and so on. And also the number of male and female bees in each generation is a Fibonacci number as well. So there's 1 female bee and 1 male bee in this generation. 1 is a Fibonacci number. In the next generation, there's 2 females and 1 male, which are both Fibonacci, 3 and 2, 5 and 3, 8 and 5, and they progress the same way as the entire genealogy does. So it's a really neat pattern that you get from the Fibonacci numbers showing up all over the place in a bee genealogy. There are other ways of looking at genealogies as well if you're looking for particular genes where Fibonacci numbers come up. And those can come up in human genealogies, where if you're tracing the instance of a particular gene, I think if you're only looking for X chromosomes, you only get one from the male parent, only have one possible one coming from a male parent, and that had to come from his female parent, but a female parent could have gotten ones from either, got X genes from both a male parent and a female parent. So it pops up that way as well in human genealogy. So talking about what Fibonacci knew about them, if you take a look at the appendix, that's the rabbit problem where the Fibonacci sequence shows up. That is from Fibonacci's Liber Abaci. That was his magnum opus, his really big book that he wrote to try to convince the merchants of Pisa to adopt our modern numbers sequence, our modern number system, and it appears in there. But it's a really cute little whimsical problem about breeding rabbits. But it's pretty short. It's only about 2 paragraphs long. And it is part of a very long chapter of example problems. So that the chapter it pops up in is in the modern translation that I have is nearly 200 pages long. In very small, it's like 10-point type. It's really small type, and they're dense, just dense pages of text. And in almost 200 pages, this problem fills about half to 3/4 of a page. So that's not a whole lot about this really famous sequence that we named after Fibonacci. So that's why I'm not sure that the Fibonacci sequence is the best option of a sequence to name after Fibonacci. So instead, let's talk about a different sequence and why I think it's a better one to name after Fibonacci. So we're going to talk about the congruent numbers. This is a set of numbers that 5, 6, 7, 13, 14, 15, 20, 21, 22, 23. And then it skips a few numbers again and then hits some more. But this particular set of numbers is a little harder to describe. So bear with me here. It's actually not that bad. It still just uses pretty basic geometry or algebraic equations to explain, but it's not quite as easy as the Fibonacci sequence in terms of how you get a number in it. So one definition you can use for a congruent number is congruent numbers are the areas of rational right triangles. So a rational right triangle is one where all of the side lengths have to be whole numbers or fractions. So for example, 3, 4, and 5 make a right triangle. You may remember that from high school. It's the classic example because it's small numbers, but it fits the Pythagorean theorem. Because you've got 3 squared plus 4 squared is 9 plus 16, which is 25, which is 5 squared. So we know that they form a right triangle because of the Pythagorean theorem. And all 3 sides are either whole numbers or fractions. So things that aren't allowed are things like square roots or pi or that golden ratio that we looked at earlier. It's illegal too because it has a square root in it. The only things we're allowed are whole numbers or plain fractions, fractions with just numbers in the numerator and denominator. So that's why these are rational right triangles. They have to have those. So if we look at the area of this triangle, the area 1/2 times the base times the height. You might remember that that formula from school as well. It's here the base is 3 and the height is 4. So 1/2 times 3 times 4. 3 times 4 is 12. Half of that is 6. So we know that 6 is a congruent number. And there it is. Here it shows up in the list. Basically, this problem is a little bit harder because I mean the explanation is still not so bad. I mean, right triangles are pretty understandable, and the requirement that the side lengths have to be whole numbers or fractions is a little harder, but not bad. The problem is trying to, if you want to say, hey, why isn't 10 a congruent number, then showing that there is no such right triangle that has all whole number or fraction sides with an area of 10 is kind of difficult. So that's the hard part about this problem. We'll see exactly how hard it is in a little bit. A second definition that you can use is that a congruent number, K is a congruent number if there are solutions to two equations, x squared plus k equals y squared. Oops. Back. And y squared plus k equals z squared. And the solutions, once again, have to be whole numbers or fractions. This idea that solutions have to be whole numbers or fractions is a theme in ancient Greek and medieval mathematics. It even pops up in some modern mathematics today in the area of mathematics called number theory, and it is very important. The field of number theory is where we get most of the computer codes that are used to send credit card numbers secretly. So it's a very important area of mathematics today, but until computers came around, it was a very useless area, and everybody was just like, it's a lot of fun, let's play with these numbers. And it didn't really have a whole lot of use until modern times. But this idea that the solutions have to be whole numbers or fractions really limits things. That means that it's possible that, for example, for a number like 10, there's no way to have a set of solutions to these equations. You can try this out with, so we showed that 6 was a congruent number in the last slide with the triangle. If you try this one with x is 1/2, you'll see that it works, and you get a number for y squared that has a square root, and a number for z squared that has a square root that is an even square root. It's not gonna, end up with a square root symbol in it. And it works to show that 6 is a congruent number. You can also look in the handout. I also worked it out entirely. If you want to take a look at that and read that through, it's got it all worked out in there. So the really hard part about this is mathematicians still do not know how to tell when a number is congruent. So if you hand a mathematician a random whole number, they still don't know if it's a congruent number or not. People are still working on this problem, and you can win $1 million for solving it. This is linked to one of the Millennium Prizes that were issued by the Clay Mathematics Institute. They issued 7 prizes for very difficult but very important math problems. And one of them, the Birch and Swinnerton-Dyer conjecture, is connected to congruent numbers. So if you solve that conjecture, then we would have an algorithm, a method of telling when any one particular number is a congruent number or not. And right now we don't have that. But what we do have is there are easy ways to tell how some numbers are congruent or not. And Fibonacci actually figured out what some of those were. So we'll talk about that a little bit later, about what Fibonacci did actually know about the congruent numbers. So the way Fibonacci got into looking at congruent numbers was he was given a quest. He was introduced to the court of the Holy Roman Emperor Frederick II, and one of the things that they did back in period, in order to know whether a scholar knew their stuff, is they were given challenge problems by scholars who were already in the court. So he was given 3 challenge problems, and one of them was basically to prove that 5 is a congruent number. He was told, basically he was given the solution to equations version of the problem, and he managed to solve it. He figured out that it works. One of the numbers you have to use for x is 31 over 2, 31 over 12. So they're pretty nasty fractions that you have to find in order to get it to work. But it's a good problem to prove that, yeah, you're a good mathematician, you know your stuff, you can solve a hard problem. And he solved those. Fibonacci solved all 3 of the problems, and then wrote about them in his book, The Book of Squares, which unfortunately he never finished. So we're not sure how much more he might have known or might have written. And he stopped at one point writing this book, and we've only got like a couple copies. He never really finished or published it. But he did, he proved that 5 was a congruent number, and then went, well, this was kind of fun. I wonder how you tell when this type of an equation has a solution, and then went on to study congruent numbers in depth in the Book of Squares. So there's some extra stuff about congruent numbers in there, not just his challenge problems. So now let's take a look at which of the 2 sequences should get the name of Fibonacci, because Fibonacci is a really cool guy. Having a sequence named after him, that sequence should be important, should say something about Fibonacci's connection to it, you would think. So first of all, Fibonacci wasn't the first to study either one of the 2 sequences. If we look at the Fibonacci sequence, it first appears in analysis of Sanskrit poetry from sometime between 200 to 450 BC. It's a long time ago. So it appears right when the ancient Greeks were first doing some of their serious mathematics. It's very old. And it appears in also more later later Indian sources as well, from the 6th century and the 9th and 10th centuries. There's a couple more sources that look at the Fibonacci sequence a little bit in those sources, mostly as analysis of Sanskrit poetry. It's possible there's some actual math in there too, but I haven't been able to get my hands on translations because I can't read Sanskrit. Since I haven't gotten the hands-on translations yet, I'm not sure exactly what's in there. He also may have learned about it from a now lost source. A lot of the problems in Fibonacci's books were taken from other sources and never attributed to other sources. There's one problem in Liber Abaci where he says, a similar problem proposed to us from a master from near Constantinople, and that's the only one that he ever attributes to anyone. But we can look at some of the Arab sources and some of the European sources and go, okay, he got this problem from this book, and this problem from this book, and this problem from this book. And so we know that he used a lot of these sources and repeated problems from these sources and never attributed them. And there are definitely a lot of sources from before Fibonacci that we no longer have, but he did. For example, one of Euclid's books is now lost that he had a copy of. And there are some of Fibonacci's own works that we no longer have. So, for example, he wrote a shorter, briefer arithmetic text than his big magnum opus because it was so big and so complicated. They said, can you shorten this a little? We don't need quite so many example problems. We don't need that algebra stuff either. It's kind of, yeah. Another thing too was that the Arab beekeepers definitely were doing a lot of beekeeping by the 9th, 10th centuries, and Arab beekeepers may have known about the link to bee genealogy, and that's where he learned his maths in North Africa, where they were doing that. So it's entirely possible that the bee genealogy was the link that Fibonacci found out about the Fibonacci sequence, and he just turned it into something about rabbits so that he would get in less trouble from the church by not quoting so much Arabic. A lot of the folks who were translating Arabic math books were omitting a lot of the Allah is so great stuff from their translations. They would edit the translations down and abridge them quite a bit to remove a lot of that for when translating to European languages. So that might have been something that Fibonacci was doing here too. But if we look at what happened with the congruent numbers, there were only 2 mathematicians who studied congruent numbers earlier than Fibonacci. There is a little bit about congruent numbers in some of the math behind congruent numbers in the Greek mathematician Diophantus, but not congruent numbers themselves. Like, he didn't look at them as a sequence. He just talked about the connection between the areas of irrational right triangles and solutions of the equations. He didn't look at anything. He didn't look at anything else with them. The 2 Arab mathematicians who studied congruent numbers earlier than Fibonacci, one of them was anonymous. We don't have his name. And the other one did not do nearly as much work on them as Fibonacci did. And we also can tell by the writing of all 3 of them, none of the 3 of them knew about each other. Fibonacci definitely didn't know about their work, or he would have put in some of the information that he didn't have that they did. For example, he didn't get the link between the equations he was given in his challenge problem and the right triangle stuff, which is fairly basic in this problem. So the fact that he didn't write about it means that he probably didn't know about their work. So there's pretty good evidence that he studied these independently of the previous mathematicians. And he knew about more about congruent numbers than either of the 2 of them. He added more congruent numbers to the list than they had. He also wrote about more facts about congruent numbers than either one of them did. And we'll talk a little bit more about some of those facts later if we have time, but I have a feeling I'm going to run out of time. So the next thing to look at, how much did he study each sequence? So for the Fibonacci numbers, we don't really have any proof that he studied them at all other than writing about that one problem. I mean, it's 2 paragraphs long. It's pretty short. If you read the problem too, it's kind of a contrived and unrealistic setup. I mean, rabbits usually don't have, when they have a litter, they usually have a lot more than 2 rabbits in the litter. Having only 2 and 2 every time is kind of unrealistic. Also, you wouldn't want to breed those 2 siblings together every single generation either. You might want to do it for one generation to lock in a particular trait of the rabbits that you really want to keep, but you definitely don't want to keep the inbreeding going much past that. So that's kind of a thing that you want to be very careful about in the breeding. And also, if you notice, it's not very well explained. He didn't manage to write a definition. Like, he almost starts explaining how the problem works in the process of giving you what the problem is. Like the explanation is really not, the write-up is kind of poor. So it's and compared to a lot of his other stuff that he writes up very well, it's kind of a strange thing. So he didn't really study this sequence at all that we can tell. For the congruent numbers, though, he definitely studied them quite a bit because he wrote the whole book of squares about them. And his other challenge problems, he proved a lot more facts about them than other people did. And then the other point to look at is how much did Fibonacci know about each sequence in terms of facts he knew about them, whether he studied them closely or not. The Fibonacci numbers, he probably didn't know very much about them. He only wrote 2 paragraphs about them. And this is a guy who wrote extensively about almost all of the math he knew. Basically, what modern math historians say is that if you take Euclid's Elements, you take Fibonacci's book Liber Abaci, his magnum opus, and you take his Practical Geometry, which is a surveying manual, you basically have 95% of all mathematics known at the time of Fibonacci. Just those 3 books, his 2 and Euclid's Elements. And that's extensive. If that's most of the mathematics known at the time, that's probably all the mathematics Fibonacci himself knew. So so most likely he didn't know anything else about Fibonacci numbers than just what he wrote about in the rabbit problem. So it's pretty good evidence that he didn't know anything about it. About the congruent numbers, though, he knew more than anybody else at the time. I mean, nobody else before him did as much as he did. And some of the things that he proved, I guess I do have a minute to talk about those. So some of the cool things that he knew that he figured out that other people hadn't was that the product of a congruent number and a square is a congruent number. For example, if you go back to the congruent number list, we talked about how first of all, we talked about how he had to prove that 5 was a congruent number for his challenge problem. But the number 20 is also a congruent number. And 20 is 5 times 4. 4 is a perfect square. So you can, and it's actually pretty easy to prove that if you've got a perfect number, multiplying it by a square, so 5 is 5 times 20. 20 is 4 is 2 squared. So if you take the triangle you have for 5, then you can get and you lengthen each of the sides twice as long as they were before. Basically, multiply each side length by 2. It's still going to work in the Pythagorean theorem because you're just multiplying the whole equation, both sides, by 2 squared. It's still a rational right triangle because all the side lengths are still going to be whole numbers or fractions. And the area is going to multiply by the square of 2 or 4. So that's where this comes from. So it's a pretty easy thing to see if you're on the triangle end of the thing. Another thing that he proved was that squares themselves are not congruent numbers. So 4 is not a congruent number. 9 is not a congruent number. 16 is not a congruent number. And so on. That one's a little harder to prove, but it's not too tough. And then another thing that he proved, and this is basically the easy way of proving that 7 is a congruent number. And I go through how to do that in the handout if you want to see the detail. Basically, if 2 whole numbers and their sum are squares. So, for example, 9 and 16 are whole numbers, and their sum is also a square. 9 is 3 squared, 16 is 4 squared. Their sum, 25, is 5 squared. And their difference, 16 minus 9, is 7. That is also a congruent number. So that's another thing that Fibonacci proved. That is a pretty neat and easy to state thing that he proved about them. So because of that, my conclusion is that if I were to go back and rename the sequences today, Fibonacci wasn't the first one on either sequence, but he definitely studied the congruent numbers independently of other people where he might have gotten the Fibonacci sequence from another source. There's some fairly good evidence that he would have. Secondly, he studied the congruent numbers in depth, but he did not do so with the Fibonacci sequence. And he also knew a great deal about the congruent numbers, but he didn't write almost anything about the Fibonacci sequence when he wrote tons about everything he knew. So I think that the congruent numbers are a better option for naming a sequence after Fibonacci. It's the stuff that he studied in depth. It's really the sequence he cared about. The rabbit problem was a cute little throwaway problem in the middle of a big, long chapter of example problems. The congruent numbers, I think, is what should be named after Fibonacci. However, the realistic thing is that the Fibonacci sequence has been named after Fibonacci for so long that there's no way that any of this would be renamed today. But I think it's an interesting thing to think about, is that what should be named after someone. So the other thing too, the cool thing though, is that the name congruent number actually was coined, the Latin version of the term was coined by Fibonacci. So we do actually use a name that he gave to that sequence. So we at least have that much. So that's at least something that we get from the whole process of looking at all of this. So in any case, that is all I have for the presentation. There's more stuff in the handout. There's also more stuff I could show you on the internet. If anyone wants to ask any questions or discuss any of things that I talked about, or
the first question I have is, what was the Latin name that he gave to the sequence that you just mentioned?
Right. The Latin version is like I don't know, congruo or something like that. It's
okay.
like the ending is similar.
Okay.
Yeah.
I do have I picked up your paper in one of the last events that I attended, so and let others go while I formulate some of the questions I had.
Sure. Anyone else have a question?
Let me get the right glasses on. On here, you didn't really explain what the Fibonacci's numbers were versus the sequence.
Oh, the numbers are the numbers that appear in the sequence. So sequence is a technical term in mathematics that the numbers in the list go in this order, and numbers could reappear in the sequence. In this case, they don't generally. But the Fibonacci numbers are the numbers that appear in the sequence.
So they're the same.
Yeah, essentially. There's a slight technical difference to it, but it's not that important for talking about them.
Okay.
Saying the word sequence when you want the order of them to be important is important, but that's it.
Okay. Also, when I picked up your handout, you didn't have your name on it.
Yeah, I know. I think that I originally had this from a template I used for a competition where things had were required to not have names on them.
Oh, okay.
I had to remove identifying information, so and I forgot to put it back in before I then printed out stuff to give as giveaway at events. There may be some slight changes between what you have from a previous event and what I put on the internet for today. There were a couple of things that I edited as I was putting it together for folks to be able to download.
No, I'm good with this. That's all my questions.
Okay. So, anyone else? Questions you want to talk about? Questions about Fibonacci? Some of the other stuff that he did?
Thank you.
You're welcome. Thanks for coming out for math history. I usually tend to not get very many people to come to my stuff because not very many people are that interested in math. So
Thank you so much for teaching.
no problem.
Well, if we are all set, then I am going to turn the microphone off, or the recorder off.
Alrighty.